Welcome to AI Paper Podcasts. Have you ever wondered how those powerful LLM agents can move beyond, simple queries? How they tackle truly complex, multi-step tasks without getting stuck in frustrating loops or just endlessly repeating mistakes?
Yeah, it's a massive challenge in AI right now.
But today, we're diving into a really interesting paper that offers a powerful solution.
We're looking at SE-Agent, self-evolution, trajectory optimization, and multi-step reasoning with LLM-based agents. And the core problem it tackles is, current LLM agents are impressive, sure, but they often fall short on these really intricate tasks.
Why is that?
Because they don't fully use the learning potential that's kind of embedded in their own problem-solving attempts. The paper calls these trajectories. Existing methods, like Monte Carlo tree search, they tend to treat these paths independently.
Oh, okay, so they miss the connections.
Exactly. That leads to limited diversity in solutions and, often suboptimal outcomes.
And that's where SE-Agent comes in. It's described as a novel framework. It lets LLM agents iteratively optimize their reasoning processes.
Right. Think of it like an agent learning from its own past attempts, but also from other potential solution paths. They can continuously improve and adapt.
How does it do that, this self-evolution thing?
It uses three core operations. First, revision. That's where agents reflect and improve their individual attempts.
Like editing your own work.
Pretty much. Then there's recombination. Here, they intelligently combine the best parts of different solution attempts.
Mixing and matching.
Exactly. And finally, refinement. That's where they optimize and select the most promising solutions from this sort of evolving pool.
And the results. Have they shown it works?
Oh, yeah. The impact's been pretty significant.
Sure.
State-of-the-art performance, they're reporting up to a 55% relative improvement on the SWE-bench Verified benchmark.
Well, that's the one with real-world GitHub issues, right?
That's the one. Super challenging. So, yeah, it really seems to help LLMs, as the paper says, transcend their initial performance boundaries.
Okay, so in this deep dive, we'll unpack exactly how SE-Agent manages this self-evolution, look at those impressive results, and figure out why this really matters for the future of AI agents. Let's get into it. So, we've all seen LLMs do some, frankly, amazing things. Understanding language, generating pretty complex code.
Absolutely.
But when you give them tools, let them interact with environments, basically turn them into agents, they hit this new frontier, these really complex, multi-step tasks.
Right, and these aren't simple single-turn questions anymore, are they?
Not at all.
Yeah, unlike a quick search query, these complex tasks need multi-turn interactions. Gathering info, reasoning, taking actions, getting feedback from the environment. This whole back and forth process forms what they call a trajectory.
A trajectory.
Yeah, basically a sequence of states, actions, and feedback. And these trajectories, they're incredibly rich. They contain all these problem-solving patterns and strategies the agent tried.
Okay, so if these trajectories have so much valuable information locked inside, why are the current methods for LLM agents still hitting a wall sometimes? What's the fundamental problem?
It's a really good question. The paper points out that the prevailing methods, things like Monte Carlo tree search, they're good at balancing exploration and exploitation, that's true, but they often treat these trajectories as largely independent things. They miss the rich interdependencies and potential synergies between different solution paths.
So they don't learn from each other's attempts.
Not effectively. And what's maybe even more problematic, the paper argues, is that even when you try to sample diverse starting points, the agents tend to converge on very similar solutions. They might differ in superficial ways like wording, but the underlying logic is often surprisingly homogeneous.
Why does that happen?
Well, the researchers suggest it stems from the inherent nature of probabilistic language models themselves.
Can you elaborate on that? Why do LLMs naturally limit diversity like that?
Sure. Think about how LLMs work. They're designed to predict the most likely next token or sequence based on this massive amount of training data.
Right, the highest probability paths.
Exactly. And that natural tendency can inadvertently funnel them into these well-trodden, often suboptimal pathways. They're great at finding the obvious answer, the common pattern.
But maybe not the most creative or truly correct one if it's a bit unusual.
Precisely. If the best solution lies off that beaten path, they might struggle to find it. This effectively constrains the diversity of the search space and stops agents from genuinely exploring novel solutions.
Okay, that makes perfect sense. And this is exactly where SE-Agent comes in. It's not just tweaking parameters or just generating more and more attempts.
Yeah, it's much deeper.
It's about actively intervening and optimizing at the trajectory level itself. How does it even start this evolutionary process?
You've nailed the core innovation there. The whole philosophy behind SE Agent is about leveraging the collective intelligence that's embedded within multiple reasoning trajectories. The goal is to overcome those limitations we just talked about. It sees this as an evolutionary process, systematically improving solutions over iterations, getting away from just isolated, disconnected attempts.
So how does it begin? Where does the initial set of attempts come from?
It starts by generating a diverse pool of what they call pilot trajectories. These basically serve as the initial genetic material for the evolution process.
Okay, but how do they make sure this initial pool is genuinely diverse, not just variations on the same theme?
Good point. They use two complementary approaches. First is multi-planning exploration. This involves varying things right at the start, different planning strategies, different prompting techniques, different reasoning approaches, just to ensure broad coverage of the solution space from the very beginning.
Like trying to solve it with completely different mindsets each time.
Kind of, yeah. And second, they use mutation-based diversification. Here, they apply controlled, targeted mutations to existing trajectories. So altering specific reasoning steps or actions or maybe intermediate conclusions just to introduce calculated variation.
So exploring broadly and tweaking finely.
Exactly. This dual approach ensures the starting pool isn't just large, it's truly varied. It gives the evolution process good material to work with.
Okay, so we have this diverse pool, our genetic material. How does the self-evolution actually happen? You mentioned three operations. Let's start with the first one. Revision. That focuses on individual attempts.
Right. Revision is all about enhancing individual trajectories through introspection. The agent basically performs a critical reflection process on each trajectory. It analyzes its strengths, its weaknesses, areas where it could potentially improve.
Like reviewing its own logic.
Precisely. And based on these reflections, it derives revised trajectories. It might eliminate redundant steps, fix logical inconsistencies, maybe incorporate alternative perspectives it didn't consider initially.
So it's like the agent saying, okay, looking back, I could have done that step better.
Exactly. And this directly fights that LLM tendency to get stuck in similar unproductive loops. It forces a genuine internal self-correcting cycle for each attempt. The paper calls this planning origin and reflective evolution.
Okay, so revision helps an agent refine its own path. But you often get breakthroughs by connecting different ideas, right? Yeah. How does SE Agent enable that cross-pollination you mentioned, the recombination?
That's where the collective evolution really kicks in. Recombination facilitates this cross-trajectory learning using three pretty powerful strategies. First, there's crossover. This is where they identify high-performing segments, like good chunks of reasoning, from different trajectories and combine them.
Creating new hybrid paths.
Exactly. Paths that inherit strengths from multiple parents. It's like mixing and matching the best bits from different approaches.
Cool. What else?
Second, transfer learning. This is more about systematically transferring specific knowledge or strategies from successful trajectories to improve the ones that are maybe less developed.
So if one agent found a clever trick,
others can learn it and apply it? Yeah. And third, there's restructuring. This is a bit more holistic. It synthesizes entirely new trajectories based on global insights drawn from the entire pool. It looks for common sub-goals, shared structures, things like that, to create novel, optimized reasoning processes that might not have been obvious from any single original path.
Wow, okay, so we're revising individual paths with revision, and then mixing, matching, and learning across paths with recombination. But with all this change happening, how does the system know what's actually better? How does it select the best paths to keep evolving? That must be the refinement phase.
Absolutely crucial, yes. The refinement phase is all about optimization and making the final selection. It uses this quite sophisticated multidimensional reward function to evaluate the quality of each trajectory.
Multidimensional, so it's not just a simple pass-fail.
Not at all. It's a much more comprehensive assessment based on three critical axes. First, task completion. This measures how effectively the task is actually solved. Using objective validation, like did it generate a non-empty code patch, did it perform enough editing steps, things you can measure directly.
Okay.
Second, reasoning quality. This evaluates the logical coherence, the depth, the robustness of the reasoning process itself. Is the thinking sound?
Right.
And third, efficiency. This quantifies the computational cost. How many reasoning steps did it take? How many resources did it use?
And how do they measure all those different qualities? especially the reasoning quality one. That sounds tricky. Is it automated?
It's a clever mix. The reward function uses rule-based auto-eval for the objective stuff, quantifiable metrics like passing unit tests or checking code syntax. But for the more subjective qualities like logical coherence and reasoning depth, it uses LLM-based expert eval.
Using another LLM to judge the first one's work.
Essentially, yes. Leveraging a separate, potentially more powerful LLM to provide that assessment, this gives a really holistic score for each trajectory.
Okay, makes sense. So then how does SE Agent actually pick the fittest trajectory, the one to move forward with or be the final answer? Is it just the one with the highest score?
Not quite just the highest score. They use a strategic selection mechanism. It carefully balances both trajectory quality based on those comprehensive reward scores and diversity.
Why diversity too?
To avoid getting trapped. If you only pick the absolute best score each time, you might converge too quickly on a good but not great solution, a local optimum. Maintaining some diversity keeps options open.
Got it.
So it continuously updates this trajectory pool, letting the best solutions rise to the top while ensuring enough variation remains. And then ultimately, the highest rewarding trajectory is selected after a set number of evolution cycles, or maybe when things stop improving much.
That's where the collective competition and genetic emergence idea comes into play.
Precisely. The whole pool competes and evolves, and the best solution emerges.
Okay, the theory sounds really solid, but, the proof is always in the pudding. The paper tested S-Agent on SWE-bench Verified. For listeners who might not know it, what exactly is that benchmark?
Right. SWE-bench Verified is, it's a tough one. It's specifically designed for evaluating code generation and bug fixing agents. It's got 500 real-world GitHub issues, and these are meticulously curated to test functional bug fixes.
Actual bugs from actual projects.
Exactly. Each issue comes with the natural language description, the code repository, and crucially, correctness is verified using the original developer-written unit tests. So it's a very realistic testbed. It really mirrors the challenges software engineers face. If your agent can solve these, it's doing something genuinely useful.
Definitely sounds challenging. So what metrics did they use to measure success there?
They use two main metrics. Pass at 1, which is simply the percentage of issues resolved correctly on the very first attempt. That shows direct, immediate effectiveness.
Okay, straight out of the gate.
Yep. And pass at 5. This looks at success within 5 attempts. It gives you a sense of the agent's search efficiency, especially when you might have budget constraints on API calls or compute time.
Right. How well does it find a solution if it gets a few tries? Makes sense.
Yeah, those two together give a pretty comprehensive picture of capability and efficiency.
So, the big question, how did SE Agent actually do against other leading frameworks? Did it live up to the promise?
The results were, pretty compelling. SE Agent consistently outperforms strong baselines, things like SWE Agent, which is based on Kodak, and SWE Search, which uses MCTS. And this was true across all 5 different LLMs they tested.
Which models did they use?
A good mix. Some open source ones like DeepSeek v3, Qwen 2.5, Llama 3.1, and also top closed source ones like GPT-4o and Claude 3.7 Sonnet.
And the numbers?
Pretty significant gains. For example, compared to SWE Agent using Llama 3.17b, SE Agent showed a plus 112% relative improvement.
Wow, double.
Yeah. With GPT-4o, it was an plus 80% improvement, and with Claude 3.7 Sonnet, plus 51%. Even against SWE Search, which is a stronger baseline using MCTS, the average gain was still an impressive plus 30%.
That consistency across different models is really key, isn't it?
Absolutely. It highlights that SE Agent's approach offers general benefits. It's not just tied to one specific model architecture that's critical for real-world usefulness.
They also did an ablation study, right, where they removed parts to see what matters most. What did that show?
Yeah, the ablation study was quite revealing. It basically showed that all the main components of SE Agent are important. If you removed either the revision operation or the recombination operation, performance dropped noticeably. It underscored that both individual improvement and collective learning are contributing.
Any particular insight?
What was particularly interesting, I thought, was that the revision step proved especially effective. The reason seems to be that it ensures you have a diverse set of trajectories before you start combining them in the recombination step.
So revision feeds recombination with better, more varied material.
Exactly. It helps prevent the whole process from getting stuck in those local optima we talked about, just exploring minor variations of the same flawed idea. There's a Venn diagram in the paper that shows this quite dramatically. SE agent uniquely solved 12 issues that none of the other baseline models could crack.
That really demonstrates its distinct problem-solving power.
For sure.
It sounds incredibly effective, but also potentially resource-intensive. Did they look at efficiency? Like how many attempts or trajectories it needed?
They did, and actually their hyperparameter analysis showed something quite encouraging. SE Agent achieves near optimal performance with just 10 candidate trajectories.
Only 10. That sounds pretty efficient.
It really is. It demonstrates the power of its trajectory-based search, and especially those inter-trajectory interactions, the revision and recombination. You don't need hundreds of attempts. They also showed it consistently outperformed the baselines even when given the same API cost budget.
That's a huge practical point.
Definitely. You're getting more bang for your buck, essentially. Better results without necessarily spending more.
Okay, to really bring this home, the paper includes a specific case study, Scikit-Learn, #14629. Can you walk us through that bug and how SE Agent tackled it differently?
Yeah, this case study is fascinating. It involved a subtle but important bug in Scikit-Learn's multi-output classifier. Basically, after fitting the classifier, it failed to expose a standard attribute called classes. This then caused an attribute error later on during cross-validation steps.
Okay, so a kind of interface mismatch.
Pretty much. An expected attribute wasn't there when another part of the library needed it. What's really interesting is comparing how traditional agents, like ones based on React or MCTS, tried to fix this versus how SE Agent did.
So the typical agents, they'd probably get fixated on the error message, right? Like a developer staring at the stack trace for hours.
Exactly. That's a perfect analogy. They would cling to the stack trace, as the paper puts it. The error message pointed to a file called validation.py. So their reasoning would narrowly focus only on that file. This led them to make minor, very similar tweaks inside validation.py. These were like quick fixes. They might patch over the visible error in some simple test cases.
But they didn't fix the underlying problem.
Right. They wouldn't pass the hidden, more comprehensive unit tests because they weren't addressing the root cause. Their attempts, their rollouts were nearly identical, just trying the same surface-level fix again and again, unable to break free from that initial clue.
But SE Agent managed to avoid that tunnel vision.
How? Because it wasn't just generating independent attempts based on the immediate error. It was iteratively interacting with and evolving entire trajectories. This allowed it to explore genuinely different solution approaches. So instead of just patching the symptom in validation.py, SE Agent was able to trace the problem back further. It identified that the root cause was actually in a different file, multi-output.py.
Oh.
And the fix was simple once it found the right place. Just add a one-line fix to correctly set the class's attribute there.
A proper root-level repair.
Exactly, and that fix passed the full test suite. It was a fundamentally different and correct solution, found because the trajectory-level evolution acted almost like an implicit regularizer. It forced the search to generate novel solutions, not just minor variants clinging to the error message.
That is a massive difference in outcome. And the paper specifically notes, none of the top 3 public frameworks on SWE-bench can solve this case, except SE Agent.
Yeah, that's a powerful statement. It really highlights the unique strength of this evolutionary approach for certain kinds of complex problems.
So let's zoom out. What does this all really mean for us, for the field?
Yeah.
SE Agent seems to show a really powerful new direction for LLM agents.
I think so. It shows they can move beyond just attempting tasks to genuinely learning and evolving their problem-solving strategies. They're transcending the limitations of just isolated reasoning attempts.
Right. It feels like a shift from just generating more attempts to generating smarter, more interconnected attempts.
Exactly. It highlights the huge value in moving beyond hoping one of your independent attempts works. By actively manipulating, reflecting on, and refining these entire reasoning trajectories, we can empower agents to escape those local optimary we keep mentioning.
Foster that cross-trajectory inspiration.
And ultimately achieve much better effectiveness and efficiency, especially in these really complex environments. This paradigm shift where agents learn from their own collective experience, it's genuinely exciting.
And like you said, this isn't just about fixing software bugs, though that's obviously huge. It feels like a potential blueprint for building more robust, more adaptable AI agents across a whole spectrum of challenges.
Yeah, it's almost like instilling a form of meta-learning directly into the agent's core problem-solving process. It learns how to learn better from its own efforts.
So thinking bigger picture,
Mm-hmm.
how could this kind of self-evolution framework maybe revolutionize other fields?
Well, you could imagine it in scientific discovery, right? Agents optimizing complex research paths, maybe suggesting novel experiment sequences based on evolving trajectories of past results.
Interesting.
Or medical diagnosis refining diagnostic reasoning by evolving pathways based on patient data and outcomes. Even complex robotics, where agents need to adapt control strategies based on past physical interactions and the experience of other attempts, successful or not.
So a final thought maybe for you listening. What kinds of complex processes, what kinds of trajectories in your work or your field could potentially benefit from this kind of optimization? Where could enabling systems to learn and evolve from their collective attempts make a real difference?
Definitely something to mull over.
If you want to dig deeper, you can find the full paper and the code for SE Agent on GitHub. As always, we've put the links in the show notes for you. Thanks for joining us on AI Paper Podcasts.